Hi, everyone. Thanks for coming out tonight. I'm Travis from the Michelangelo team, like Mingxi. Up here in Seattle, one of the things that we do on the Michelangelo team that's unique to us is we work on the deep learning platform. And one of the products that we work on up here on the deep learning platform is Horovod. Horovod is an open source distributed training platform that lets you take your model that you've trained on one machine, scale it up to running training on potentially hundreds of machines, ideally without having to sacrifice any scaling along the way. So the first question I want to address is, why are we so interested in deep learning right now? So obviously deep learning is something that gets talked about a lot out in industry and the world. One of the reasons that we're very focused on at Uber is that as we look at how other models perform as the volume of data tends to increase, what we find is that deep learning, in most use cases, tends to start giving us greater and greater performance after a certain point where older models start to other models start to level out. And so for certain problem types that have lots and lots of data being collected and lots of complexity in terms of the problem space, deep learning is really the only way to go for us. And one example of that, of course, is in the research domain, we have things like self-driving cars that you're all familiar with. But one thing that I think is particularly interesting is also that we're starting to see more and more people coming from more traditional data science backgrounds, working on Spark pipelines, things like that, starting to find that deep learning is giving them a lot of benefit as well. And so finding ways to create tools for people that are accessible no matter where they're coming from in terms of their background is a big goal of ours on the deep learning team. So what makes deep learning deep? Now, fundamentally, it just comes down to you have some model that has many, many layers. But the thing that I want you to focus on when you sort of conceptualize that is that depth is what creates the expensiveness of the compute and why we need accelerated hardware like GPUs in order to process these models efficiently. Whereas with other models, we could get away with using commodity hardware, traditional Hadoop and Spark clusters, that sort of thing. As for training a deep learning model, you may be familiar with the backpropagation algorithm. It's the most common way that you do training. And one of the things that is worth sort of realizing about this is that there's very little opportunity for parallelization in backpropagation. You see here that layers 3 and 4 happen to be coincide at the same layer or level so that we could potentially update them in parallel, but the other layers depend on one another in a sequential order. And so there are fewer opportunities for parallelism, again, with something like Spark. So when we start to think about how are we going to scale this up, what we realize is that our fundamental bottleneck is that we have lots and lots of data and very complex models. And so our approach is going to be to divide the data between the workers. And why do we do that as opposed to dividing the model? Well, it turns out that even though the model is very complex, in most cases, it can still fit within the memory of a single GPU. And so in our process here that we're showing, what we're going to do is we're going to have run replicas of the model on different workers, and then have the process of computing the gradients. We're going to average them across the workers and then use those in the backpropagation steps for the individual models. And then the idea is that after processing each batch, we're going to end up with identical models on each of the replicas. And so I'll talk a little bit more about that later on. So, all right, so we want to do this. There are other frameworks that have accomplished something similar to that idea of let's divide the data and then train models in parallel. So what do we want to do differently? So there are many ways to do distributed training. One of the earlier ways was with TensorFlow. They had something that they called disbelief at Google, and they open sourced that in TensorFlow as their parameter server model. But for us, what we want to do is try to create a framework that is ideally as abstracted away from the researcher as possible in terms of the distribution. So with parameter servers and other more traditional approaches to distributed training, the researcher has to think very tightly with how they're going to be doing their distributed training at modeling time. With Horovod, we wanted to create a system that allowed infrastructure people, like those of us on the deep learning team, to worry about things like what servers are we going to use, what network gear are we going to use, container environment, et cetera, and let the researchers and machine learning engineers focus just on how do they improve the model performance of their deep learning, their deep neural network. And that's where Horovod comes into the picture. So Horovod is a library for distributed deep learning that was developed here in Seattle, originally by Alex Sergeev, who's there in the back. It works with stock TensorFlow, Keras, PyTorch, and MXNet, and provides a similar interface across all of these frameworks so that people that want to experiment with PyTorch or experiment with TensorFlow can very easily go back and forth without having to worry about rewriting their distributed training code. It's very easy to install. You just use something like pip to install the Horovod package. And it can also take advantage of accelerated hardware like RDMA for remote direct memory access, GPU direct. And like I said, it achieves our goals of separating the infrastructure from the research. Now, at the core of Horovod is the Ring-Allreduce algorithm. So this is what enables us to aggregate those gradients that I talked about across the different workers. And this was actually shown in a paper published by some folks at Baidu back in 2009 to be the bandwidth optimal algorithm for this particular problem. And the way that the sort of intuition that it exploits is that there's inherent associativity with aggregation of numbers, right? So while one worker is sending some numbers to be aggregated to the next worker in the ring, it will receive some numbers to aggregate from the previous worker in the ring. And so this proceeds circularly. And so essentially the amount of communication just grows proportional to the number of workers that you have in the ring. In terms of the overall stack, the architecture that Horovod uses, what we do is that we drive the process through an application that was ran here called Horovod Run, which under the hood calls MPI Run to launch processes across multiple hosts and different processes for different GPUs. And then below that, you have your normal TensorFlow code, PyTorch code, MXNet, what have you, that defines your model, and as well as some additional Horovod decorator stuff that we'll show you. And then we have custom operators that we've written for these various frameworks that as part of their backwards pass, they will submit their gradients to a queue in Horovod, and then the Horovod system that sits underneath will consume tensors from that queue and attempt to perform aggregation. So what happens there is in what we call the control layer there, each of the workers will submit over MPI the tensors that they currently have available to what we call the coordinator node, which is going to be rank 0, just one of the processes kind of arbitrarily. And then the coordinator will determine, okay, of all the tensors that you've asked me to process, this is the set that's ready to go. So this is the set that I want you to process. And then each of the workers will process the same set of tensors in what we call the data layer below. And the data layer is very versatile in the sense that you can use a variety of different frameworks. Currently supported, you can use MPI as well, but you can also use Nickel, which allows you to exploit both RDMA and GPU aggregation, and DDL as well. And in the future, we're going to support Glue, which is a framework developed by Facebook for doing collective communication. And how does this end up working out in practice? It scales very well. So what you see there in the white bars are the ideal scaling performance. So that would be for every 1 unit of compute that you add, you would get 1 additional unit of performance in terms of images per second. And Horovod tends to scale at about 90% of that in practice when you combine it with RDMA. And that goes up to hundreds of GPUs we see in practice on common models like Inception and ResNet 101. So that's the sales pitch for what Horovod is, why it works well. So now let's get into how you can start using Horovod today. So how to use Horovod. All right. So the first thing you want to do in your Python script is you just want to call import horovod.tensorflow or whatever your framework is as HVD. And then you want to initialize it, hvd.init. Next up, you want to pin your process to a GPU. So what does this mean? Well, what it means is that when you're running your MPI process and you have all of these blue processes here running, in order to make the best use of your GPUs, we only run one process per GPU that you have. And so what this little line of code here that says config.gpu options.visible device list equals local rank is doing is it's just saying, give me the GPU whose index is the same as my index as a process in MPI on this node. And so the effect is that you get exactly what you see there, that process 0 on worker 1 will get GPU 0 and process 1 will get GPU 1, etc. Okay, so the most important thing to do is right here, where you wrap your optimizer, which can be any optimizer that you want to use, like Momentum, SGD, Atom, and then you just wrap it in what we call the Horovod distributed optimizer right there. So what that will do is it will not make any modifications conceptually to your optimizer, but it will do this magical aggregation of the gradients across workers for you. And one other thing I want to call out here that's very important is less of a Horovod API specific thing and more of a how you do distributed training practically thing, which is scaling the learning rate. So you see we also have a line here that says learning rate equals or multiplied by Horovod.size. And so what that does in effect is account for the fact that you'll be averaging the gradients across workers. And so your effective batch size is actually going to scale with the number of workers you have in the system. And it turns out that there have been several papers written on this that found that scaling the batch size, that allowing the batch size to grow, but scaling the learning rate actually does tend to give you good performance. But there are some caveats that people run into. So one thing that you typically want to do is you'll want to do what's called learning rate warm-up, where you'll want to keep the learning rate a little bit lower for the first few steps and then allow it to grow after a few warm-up steps. And if you're using our Keras API, we provide actually for you some callbacks that you can just hook into that will take care of all of this for you. Next up, you want to synchronize the initial state. So this is what we call broadcasting the global variables. So you have some model that has some initialization of the parameters, and you want to make sure that's the same across all the workers. So by performing this broadcast global variables, that will take care of that for you. Now, the question that you might have is, why do we necessarily want to do that? And this comes back to that idea that we want the models to be identical across all of the replicas, right? So at initialization time, if you're using some random weights drawn from some random distribution, they're necessarily going to be different across the replicas unless you have the same seed. And so what can happen is what you're seeing there is that the red lines indicate the average gradients between A and B, but they're going to be heading in different directions if the models started in different points. So what we want to do is we want to broadcast the global variables so that A and B are in that space located at the same point, and we don't have to worry about them diverging into different parts of the parameter space. And finally, very simple step is just to checkpoint only on the first worker. So mostly the motivation for that is that it's theoretically should be redundant to checkpoint on more than one worker because the model replicas should be the same. Now, the part that has come up a few times is how we do the parallelism. So data partitioning is one approach. It's the one that I think comes most naturally to most people. You shuffle the data set, and then you split the data across the workers in some uniform way. And then each worker trains on just the partition that it has. And then after each epoch, you reshuffle, you repartition, you do it all again. So this will work, works fine. The one thing you want to make sure of is, and this bites a lot of people sometimes, is that all the partitions need to give you the same number of batches on each worker, otherwise you reach a deadlock state. This is something that we're actually looking into ways of getting around, but at the moment it's a reality for people. And the reason why you can imagine that this would happen is that because this process is proceeding sequentially, if one of the workers finishes all of the work it has to do and it moves on to the next epoch, while the other workers are still trying to submit tensors to be aggregated, then they're going to be waiting for this worker that's off doing something else, and they're never going to make progress, and the system will come to a halt. So just be sure your batch sizes, or your batches are the same between workers. But there's an alternative, which is random sampling. So as opposed to partitioning the data set, you still shuffle it so that your batches are going to have different workers between, or different examples between each epoch. But then each worker is just going to take a random batch for each step. And then you run on a fixed number of steps per epoch. And you might say, well, how does that work out in practice? I mean, doesn't that mean that different workers could potentially process the same batches? And yes, that is true, but what we found empirically, and there have been some papers written on this as well, is that in practice, it typically yields the same results. And the reason for that is that if you have a very large data set and the examples are all roughly the same quality, what we find is that it's effectively the same as just partitioning the data, and having potentially some small probability of seeing the same example twice doesn't actually really hurt you, particularly because the probability goes down as your data set increases, right? So the conclusion on that note is use whichever is most convenient for you. We typically find that random sampling is the easiest to get going initially, but partitioning may fit better into your use case, in which case we recommend systems like Petastorm, which is a system developed here at Uber for doing distributed data parallelism that can take care of data partitioning for you. And one thing to call out is that validation can also be distributed. There are just some extra caveats there that you need to watch out for as well. But Horovod provides something, the metric average callback, that will help you take care of that. And here's a full example just to kind of drive it all home of what training would look like with Horovod. So called out in bold are the parts that are unique to Horovod. We're going to initialize it, pin the GPU, scale the learning rate, wrap the optimizer, broadcast our global variables, and checkpoint on the single worker. And then we sort of throw those into our monitored training session and run our model. But wait, there's more. So I told you about horovod.tensorflow, but there's also horovod.keras, horovod.tensorflow.keras, .torch, MXNet, and more frameworks are on the way. We support graph execution as well as eager mode in TensorFlow, which is something that is pretty unique to distributed training frameworks. Most of them don't currently handle that. And how do you run run Horovod? So mentioned Horovod run. You can pass in NP to be the number of processes you want to run total. And then you give it -H, which tells you the list of hosts and the number of processes to run per host. So you can run non-homogeneous training. You could potentially run 2 processes on one host and 4 on another. And that's what we see here in the multi-node case, is how you specify the distribution of processes across different hosts. So we have server 1 takes 4 processes, server 2 takes 4 processes, etc. Under the hood, this is actually doing a lot for you. So this is going to be calling MPI run, but it's also going to be detecting which interfaces are compatible between the workers, so that you don't have to worry about specifying the often very verbose number of arguments to MPI, which often is a trial and error process to determine, okay, which interfaces are compatible, which should I be using, what flag should I be passing in. But going beyond that, we can also run Horovod on Apache Spark. To run Horovod on Spark, all you need to do is create your normal Spark context, and then you define a training function, which we do in cell number 3 there. And then finally, we just call horovod.spark.run, and it will go ahead and execute that in a distributed manner using Horovod. So why do we want to support Apache Spark? Well, like I mentioned at the beginning of this talk, we have a lot of people that are traditional data scientists coming from, using boosted trees and things like that, which are typically things that are supported in the Spark ecosystem, whereas distributed deep learning is not. And so we want to bring our tools to where our users are, right? And so the nice thing about Spark is that you get to take advantage of all of that infrastructure for doing your data preprocessing. And you can also use very nice interactive tools like Jupyter Notebook with Horovod for distributed training. And then, like I mentioned as well, we definitely recommend using Petastorm to sort of act as the bridge between your RDDs and Spark and then your data in TensorFlow or Horovod more broadly. So with Petastorm, what you would do is you would take your RDD or your data frame in Spark and you'd write it out to something like HDFS as a Parquet file. And then Petastorm will take care of doing the random shuffling, the fault tolerance, the partitioning, and it will even do some nice in-memory caching for you and distribute your data across workers. And the nice thing about that is that then it takes care of all of those sort of data partitioning problems that we talked about earlier. And so just to wrap up, practical results for Horovod at Uber and beyond. Horovod is now accepted as the only way that our teams here at Uber do distributed deep learning. It's the only way supported on our platform. And we've, with using Horovod, we've managed to get orders of magnitude speed ups in training both convolutional neural networks and LSTMs, all with the same final accuracy. And now it's also used by other groups, including NVIDIA, Amazon, Alibaba, Oak Ridge National Lab, and I believe in their work to do on the winning the Gordon Bell Prize, used Horovod for some of their training. And it's available in pretty much all cloud distributions. You can get AMIs for AWS, for example, to get going with it today without having to do any Docker setup or anything like that. So with that, I invite you to please check us out online, and you're more than welcome to come and ask us questions on GitHub or to contribute. That'd be great as well. We love contributions.